Yeah, so the recording is started. You can start.
All right, yeah, thanks a lot for inviting me to the seminar. So today I'm going to tell you about the PureCircuit problem, which is a new tool for proving very strong inapproximability results for PPAD. So this is joint work with Argyrios Deligkas, John Fearnley, and Themistoklis Melissourgos. So let me just try to summarize the contribution in just one sentence, which is in this work, we present a new tool for proving very strong PPAD hardness results. Now, if this sentence doesn't quite make sense right now, that's normal. I haven't defined some of the things, and hopefully by the end of this talk, this sentence will make more sense. In particular, what is PPAD? What is a very strong hardness result? This kind of stuff. So the organization of the talk will be in 4 parts. First of all, I will introduce the kind of problems that we look at. Then I will zoom in into the class PPAD specifically, which is the one that we care about here. After that, I'll introduce the PureCircuit problem, which is the new tool that we present. And finally, I'll show one application, one example of how to use this tool to get a strong PPAD hardness result. So let me just start with a general introduction. So I'll just list some problems, computational problems that I think are quite widely thought to be of interest. So the first one is the Nash problem. Given a game, let's say a 2-player game, compute a mixed Nash equilibrium of the game. Another example, even more famous, the factoring problem. Given a number, compute a prime factor of that number. Then we have a problem from topology, based on Brouwer's fixed point theorem, if you've heard of it, which is I give you a continuous function from the unit cube to itself, and I ask you to compute a fixed point of that function, namely a point x, such that f of x equals x. And as a final example, again from game theory, which is compute a pure Nash equilibrium of a congestion game. What is a congestion game? A congestion game is a type of game that's used to model traffic and how agents are going to act strategically to avoid traffic and stuff like that. So you can use it to model these kinds of situations. So I've put these 4 problems here, and even though they look quite different, they do have something in common. What do all 4 of these problems have in common? Well, it is that they are all so-called NP total search problems, abbreviated as TFNP. So they are all in this class TFNP. And what does that mean? Why are they in this class TFNP? Well, essentially they have 2 crucial properties. The first one is that they are total, meaning that for any instance of the problem, there always exists at least one solution. And the second one is that they are in NP in the sense that you can always verify solutions efficiently, namely in polynomial time. So let's go through the problems. Nash, why is Nash in TFNP? Well, there is a theorem by Nash, which is called Nash's theorem, that proves that any game has at least one mixed Nash equilibrium. And then it's not hard to see also that you can easily check if a given candidate strategy profile is indeed an equilibrium or not. Factoring, I think it's quite obvious that any number has a prime factor. So again, you get totality that way. Brouwer, well, for Brouwer, it follows by this Brouwer fixed point theorem that I stated. Any continuous function that maps the cube to itself has to have a fixed point. And the last one, the pure congestion problem. This is again a very well-known problem result in the theory of congestion games, that every congestion game has at least one pure Nash equilibrium. Okay, so for each of these problems, there is a mathematical result stating there always has to exist a solution. And as a result, these problems are total search problems. They are in this class TFNP. Now, why is that important that they are in the class TFNP? Well, it has some implications. Now, all of these problems are believed to be hard, mainly because we don't have a polynomial time algorithm to solve them. And we would like to be able to provide evidence for that. And the way one usually provides evidence that a problem is hard to solve is by proving NP hardness. Okay, so a very natural question is, okay, can we prove NP hardness for any of these problems? And the answer is, because they lie in TFNP, This is not possible unless something very surprising happens, namely unless co-NP collapses to NP. So let's look at this in a bit more detail. So this class TFNP, which was defined by Megiddo and Papathimitriou in 91, contains all total NP search problems. So let's analyze this sentence. First of all, these are search problems, meaning that you're always looking for a solution, a specific solution, not just a yes/no answer. So these are not decision problems, not the standard problems that are usually studied when you look at NP completeness and stuff like that. You're actually looking for a specific solution. Second, the problems are in NP or are of NP flavor in the sense that any solution can be checked efficiently, meaning if I give you a candidate solution, you can verify in polynomial time, decide is it a solution or is it not a solution. Okay, and finally, perhaps the most important property is totality. For every instance, there always exists at least one solution. Okay, so there is some mathematical proof that proves that every instance is always guaranteed to have a solution. This class TFNP, if you want to situate it in known classes, you can think of it as lying between P and NP, or rather between the search versions of these two classes. Okay, so how do we provide evidence that the problem in TFNP is hard? As I mentioned earlier, we cannot hope for NP hardness really, unless something very, very surprising happens, namely unless NP collapses to co-NP. We'll leave that as an exercise, but let me just mention the very brief idea of why that holds. Let's say that somehow you were able to prove that some TFNP problem, for example, the Nash problem, is NP hard. In other words, let's say that you were able to provide a polynomial time reduction from the 3-sat problem to the Nash problem. You could then use this reduction to obtain certificates even for unsatisfiable 3-sat formulas, meaning that even 3-sat formulas that do not have any satisfying assignment, you will be able to come up with a short certificate that efficiently proves that this formula does not have a satisfying assignment. And this thing then immediately essentially implies that NP equals co-NP. So in other words, if you can prove that some TFNP problem is NP hard, then you have provided short proofs of unsatisfiability. And this is it's not believed to, I would say most complexity theorists don't believe that this would be the case. Okay, so what's the next best thing? Well, for problems in NP, in order to prove that they're hard, we prove that they are NP hard and thus NP complete. So maybe we can just show that problems are TFNP hard as opposed to NP hard. Maybe we can show that they are TFNP complete. And now here it is believed that there are actually no TFNP complete problems at all because of the way TFNP is defined, namely the fact that it is so general and essentially captures all potential proofs of existence. So what this leaves us with is that we are stuck. How do we provide evidence that of some problem in TFNP, like Nash or factoring? How do we provide evidence that these problems are computationally hard? And the idea that Papathimitriou came up with around 30 years ago is to look inside TFNP, to explore the landscape inside TFNP by defining new intermediate classes between TFNP and P, and obviously classes that are nicer to work with. So one such class is PPP, and you can think of PPP as containing all TFNP problems where the existence of a solution, the fact that any instance always has a solution, this can be proved by using the pigeonhole principle. Okay, so the general idea is that we classify problems into subclasses of TFNP depending on how the existence of a solution is proved, depending on what the proof argument uses. So if the proof argument uses the pigeonhole principle, then this is a strong indication. In a certain sense, you can prove that it lies in the class PPP. Another class is the class PPA. This class contains problems where the existence of a solution can be proved by applying some kind of a parity argument. And equivalently, the class also has a topological characterization. So you can also think of this class as containing all problems where the existence of a solution can be proved by using the Borsuk-Ulam theorem from topology. For those of you who have not heard about it, it's a pretty famous theorem. It was famously used by Lovász to prove the Knežev-Lovász theorem. So some of these classes have these topological characterizations as well, meaning that you can also think of them as capturing the complexity of that topological theorem. Another quite well-known class is the class PLS. What is the proof argument corresponding to PLS? It's essentially local search arguments or so-called potential arguments. And problems that are known to be complete for this class are the pure congestion problem that I had on the first slides, and also the local max cut problem, which is I give you a weighted graph and I ask you to find a cut of the graph that is maximal up to some local change, such as swapping a vertex from one side of the cut to the other one. So finding local optima. And in general, PLS captures problems that have this local optimum flavor. And the last class I want to talk about is the one that we will mainly focus on in this talk, which is the class PPAD. So PPAD contains all problems whose existence or resolution can be proved by some sort of a directed graph argument. I won't say more about this now because we'll actually see the formal definition in a bit. So let me just mention that the class is mostly famous because the Nash problem is complete for this class. In other words, this PPAD class exactly characterizes the problem of computing a Nash equilibrium. And the class also has a topological characterization in terms of the Brouwer problem. So again, you can also think of PPAD as a class containing all problems where the existence of a solution can be shown by using Brouwer's fixed point theorem, another topological tool. So if you look at this picture, you'll see that one of the problems that I had on the slides earlier is missing, and that is the factoring problem. So the factoring problem actually, well, we don't know exactly where it lies. So I'll put it over here because we have randomized reductions to PPA and PPP. So in some sense, they are in PPA and PPP, but we have no hardness result, no lower bound. So it could very well be in P. So factoring is very much open where it lies in this hierarchy. So given this landscape of classes, what you do then is, given some problem in TFNP that you care about, for example, the Nash problem, you try to find out where exactly does it fit in this picture. So you try to show that it lies in some of these classes, and then you try to show that it's complete for that class. For example, you prove that Nash lies in PPAD, and then you prove that it's also PPAD hard, and then you have exactly classified the complexity of the problem as being PPAD hard, and similarly for other problems that end up being PLS complete or PPA complete. Now, what does that tell us about what we initially cared about, namely the complexity of the problem? Okay, so why is a PPAD hardness result, the PPAD hardness of Nash, why is that interpreted as saying the Nash problem is computationally intractable? In other words, what reasons are there to believe that PPAD is not the same as P, that PLS is not the same as P? So I can give you three reasons that are more or less convincing. The first reason, which applies to most of these things, is essentially that, okay, we have many seemingly hard problems that lie in these classes, meaning that if you could solve one PPAD complete problem, you would be able to immediately solve all of them efficiently. And so that is some kind of evidence. The problems that are seemingly hard in the sense that many people have tried to solve them efficiently and have failed in these classes, and that would immediately collapse to P if you're able to solve one of them. The second reason is that there are oracle separations between all of these classes. Now this is, more or less convincing. It depends. At least in the context of TFNP, there are no reductions known yet that break oracle separations. So as far as we know, oracle separations do give a pretty good indication. And in any case, oracle separations essentially tell you that some types of reductions will not work to obtain collapses. So it essentially, it tells you that some kind of black box reductions will not help. And finally, perhaps the most convincing type of evidence that PPAD is not equal to P is that there are hardness results under cryptographic assumptions. What do I mean by that? if you were able to show that PPAD equals P, then that would have implications for cryptography. Namely, it would mean that some things that are assumed to be secure by cryptographers will turn out to not be secure. Okay, so if you assume that some things work in cryptography, then you can deduce from that that PPAD cannot be equal to P. But this is, of course, ongoing work in trying to get these hardness results under very, very standard cryptographic assumptions that are, widely believable. So this completes the first part of the talk. Maybe I can pause to ask if there are any questions, and then I'll continue.
Yeah, I have a short one. If you go back to this diagram of classes, yes. So PPAD is in PPA, but it's also in PPP.
Yes, it's drawn correctly. Yes, indeed.
Okay, good. If you look at the intersection of PPA and PPP, could this be the same as PPAD, or is it known that there are problems?
Yes, good question. So it is not known to be equal. I don't know if there is an oracle separation indicating that they are distinct, but I would assume that something like that can probably be obtained. Okay. But let me say to be sure that, yeah, it's open whether they are equal.
Okay, but your guess will be that they're not.
Yes.
Okay, thanks.
Okay, if there are no more questions, then let me continue with the second part, which is now we're going to zoom in into the class PPAD. So let me start by just explaining why PPAD is so important to people who care about economics, game theory, and stuff like that. And the reason is that it captures the complexity of many very, very natural problems in that field. Okay, so I already mentioned the Nash problem, and this was a very celebrated result by Themistoklis Melissourgos and Chen Teng. They essentially show that computing a Nash equilibrium for a game with 2 players or more is PPAD complete. So PPAD exactly captures the complexity of this fundamental problem in game theory. And then, these results have been strengthened by looking at special classes of games, constant rank games, anonymous games, sparse games, etc. For some classes of games with many, many players, it is even possible to show constant inapproximability. For example, polymatrix games or so-called graphical games. Polymatrix games will be our application later, so we'll see a bit about that. The other very big and fundamental problem in economics is market equilibrium. Okay, that's really a very important problem. And there's a very famous model for market equilibrium, which is the Argyrios model. And again, there the question is, I give you a market with buyers and products, and you have to find a market equilibrium, namely the correct prices where everything is sold exactly in the quantity in which it is available. And there's a famous result by Brouwer saying that this always exists. And the obvious question is, how do you compute it? And then again, it turns out that this problem is also PPAD complete. And I've also put Fisher here, which is a special kind of market simpler that turns out to also be PPAD complete. So it doesn't get any easier. And a third example that I have is from fair division. So there's a very well-known problem called cake cutting, which is essentially you have a divisible resource, which is modeled as the 0-1 interval. And you'd like to divide it amongst different agents who have different opinions about which part of the resource are more valuable or less valuable. And you want to divide it in such a way that all the agents are happy with the division. They feel that they got the best part. And again, there is an existence result saying this is always possible. And the obvious question is, can you find it? Can you compute that fair division? And again, there are some results suggesting that this is PPAD complete, at least for some types of preferences. So this was like the motivation for why PPAD is very important in that field. But now let's actually get into what PPAD really is. All right, so the formal definition of PPAD. Why is PPAD a nice class to work with? Just like PLS, PPA, PPP, all the classes in the diagram. The reason is that they have nice canonical complete problems. Okay, that was a problem with TF and P. It probably doesn't have complete problems. But PPAD is defined using a complete problem, and so it trivially has a complete problem that can then be used to prove hardness results. Okay, so the class PPAD is essentially defined as the set of all TFNP problems that reduce in polynomial time to this canonical complete problem, which is called end of line. Okay, so it's just all the problems that can be efficiently reduced to end of line. What is this end of line problem? So the input to the problem is a directed graph of paths and cycles, meaning something like this, okay, a directed graph where you only have paths and cycles. So you never have out degree more than one or in degree more than one. You only have paths and cycles in this graph. And I also give you a source, maybe one of the sources. For example, I give you this source. Okay, so the input for the problem is this graph and this particular source, the blue square. What is the goal? What are you supposed to compute to solve the problem? We have to find any sink, I don't care which one, or any other source. Again, I don't care which one. Okay, so the solutions are all the red stars in this picture. So this would be a solution because it's a sink. This is another sink. This would also be a solution, sink. And this would be a solution because it's another source. This is also another source. That would also be a solution. This is not a solution because this is the original source. Okay, so I want a different source or a sink, any sink. Okay, so I'm happy with any, you give me any one of the red stars and I'm happy this is, you solve the problem. Now, if I just define the problem like this, there's a bit of an issue, which is that the problem is clearly polynomial time solvable. Okay, if I just give you the graph explicitly and I tell you find a sink, you can just check every vertex and solve the problem efficiently. But I said earlier that PPAD is believed to be, a hard class. So what's going on here? Well, there is a catch, which is that the graph is not given explicitly. Okay, I don't give you the graph explicitly in the input. I give you the graph in some implicit way. Namely, the vertex set is actually exponentially large. Okay, so it's all bit strings of length n. So there's 2 to the n vertices. And I also give you 2 Boolean circuits S and P that you can use to compute successors and predecessors in the graph. What do I mean by that? If we look at this node over here, okay, if I give this as input to S, then S is going to output the ID of the next node, okay, the successor node. And similarly, if I give this input to the P circuit, then I will get the ID of the predecessor node. In other words, these Boolean circuits, they allow you to efficiently take small steps in the graph. Okay, so you can explore the graph one step at a time, where each step is polynomial time, but the size of the graph is exponential. So if you wanted to just explore the whole graph, that would take exponential time. Okay, and this is why the trivial algorithm of just starting at the blue node and just following the line, in the worst case, that will take exponential time. So the end of line problem just tells you, given a graph of this type that is represented implicitly, meaning that it has exponential size in its representation, find any of the red stars. I don't care how you find it, whether you follow the line, whether you somehow guess the right position. I don't care how you find it, but that's the goal of the problem. And now, obviously, it's no longer clear if this is polynomial time, and it is believed that it cannot be solved in polynomial time. Maybe let me just pause here again to see if there are any questions about this definition, which is perhaps a bit unusual.
I have a small one again.
Mm-hmm.
So in theory, you're allowed to do with these circuits whatever you want.
I give you the code of the circuits. I give you
Okay.
the full representation of the circuit, so you can look inside, look at the gates, you can do whatever you want. Yes.
Okay.
Yes, exactly. If these things were represented as black boxes, oracles that you could just query, then it's easy to show a query lower bound, an exponential query lower bound.
Yeah.
But because we need to work in the standard Turing machine model here, not as some query thing, if we want to capture the complexity of problems like Nash, which are completely, white box problems. For this reason, you need to have a definition of the problem that has this kind of circuits you need to have the code of the successor and predecessor functions.
Okay, thanks.
Yeah, in a certain sense, the question of whether this problem can be solved efficiently is exactly, can you do anything with the code? If I give you the actual code of these circuits, does that help you in some way to solve the problem or not? And it is believed that it does not help, but that seems very hard to prove. Okay, so this problem, which up to this point looks pretty natural, but once you introduce this, starts looking quite artificial. Surprisingly, it turns out that this problem exactly characterizes the complexity of all these natural problems that I mentioned earlier. And this is really at first a surprising fact, that you have a problem like this defined with circuits and stuff like that, that ends up exactly characterizing the complexity of problems like computing Nash equilibrium or market equilibrium, which are completely natural problems that don't have circuits, Turing machines in the definition or anything like that. Okay, so the next question is, okay, this is the definition of PPAD. How do we prove PPAD hardness? And the answer is, okay, we have to reduce from this end-of-line problem. We know that this problem is, by definition, PPAD complete. So in order to prove that some problem, like the Nash problem, is PPAD hard, we have to come up with a polynomial time reduction from end-of-line to the Nash. So let's take a look at what a reduction means in this setting. And for that, let's take a look at what a reduction is in, first of all, in the standard, NP hardness, standard NP hardness proof, the way we prove NP hardness for decision problems. And that is by, for example, reducing from the 3-sat problem, which is known to be NP complete. So what is the definition of a reduction in that setting, in the NP hardness setting? So we say that 3-sat reduces in polynomial time to problem A if there exists a polynomial time function f that takes an instance of 3-sat, transforms it into an instance of the problem A, and then what you want in order to say that the reduction works is that for any instance of x that you started off with, x is a yes instance if and only is a yes instance for 3-sat, if and only if f of x is a yes instance for the A problem. Okay, and why is a reduction defined this way? Because you want this intuition to hold. If I could somehow solve problem A, then I would be able to solve 3-sat. And this equivalence here ensures that this is the case. Okay, no matter if f of x is a yes or no instance, you will immediately know if x was a yes or no instance for 3-sat. So now we want to take this and adapt this to our setting, namely to proving PPAD hardness. And in order to do that, we're going to replace 3-sat by the end-of-line problem. And just to make things precise, I'll say that the problem A we're trying to prove hardness for is the Nash problem. So let me just take this definition and blindly replace 3-sat by end-of-line everywhere and replace A by Nash everywhere. Then I get this thing. Okay, so end-of-line reduces to Nash. That means that there's a polynomial time function that takes an instance of end-of-line, constructs an instance of Nash, and then we have this equivalence. Now, if you look at this for a bit, you'll see that there's a bit of an issue here, because this statement actually is vacuous. It doesn't say anything. X is a yes instance of end-of-line if and only if f of x is a yes instance for Nash. Well, the problem is here we have total problems. So all instances are yes instances. So this is not saying anything. So if we go back to the intuition of what we actually want to be able to say, namely, if we can solve the Nash problem, then we want to be able to solve the end-of-line problem. Okay, this is what our reduction should give you. Then we need to modify the definition as follows. We still have a function f that maps an instance of end-of-line to an instance of Nash. But now what we want is that given any solution y to the constructed instance f of x of Nash, we want to be able to efficiently obtain a solution to the original instance x of end-of-line. So another way, the reduction has two functions. First, a function f that takes an instance of end-of-line, constructs an instance of Nash. And then you have another function that, given any solution to the Nash problem, efficiently finds a solution to the original end-of-line problem. Again, the goal, the intuition for this definition is just ensuring this thing at the bottom, that if we can solve the Nash problem in polynomial time, then we'll also be able to solve the end-of-line problem in polynomial. All right, so this is essentially the definition of a reduction in this setting. And now let me say a bit about how people were actually able to prove that the Nash problem is PPAD hard. So essentially what they were able to provide is a reduction, polynomial time reduction from end of line to the Nash problem. But if you look a bit at this end of line problem, it's not very easy to reduce from. And I don't think most people would know where to start such a reduction, starting from this weird artificial end of line problem, to go to a natural problem like Nash. And so what these people actually did is that they had multiple intermediate steps. So they took this artificial end of line problem and they first reduced it to a less artificial problem, namely a version of the Brouwer problem, this topological problem that I mentioned, which is based on Brouwer's fixed point theorem. So what this first step of the reduction achieves is it takes this unstructured graph and gives it some topological structure. Okay, that's the first step of the reduction. And then the second step of the reduction, what it essentially does is that it transforms this topological problem into some kind of a constraint satisfaction problem, into a set of constraints that need to be satisfied. And this is a so-called generalized circuit problem. And then the final step takes this generalized circuit problem and reduces it to the Nash problem. And this can be thought of as taking a problem with some kind of constraints and constructing a game, namely a specific instance of Nash, where these constraints are necessarily enforced at any Nash equilibrium of the game. Now, this was the first reduction that showed a PPAD hardness result for a natural problem, and subsequent work has reduced either from the Nash problem or from the problem right before that chain of reduction, namely this generalized circuit problem. And so this new tool that I'm going to present next, it actually replaces this generalized circuit problem. It's I would say a severely simplified version of this generalized circuit problem that allows you to get very strong results. So this is what this generalized circuit problem looked like. I don't expect you to read this, just to see that there are many different types of gates or constraints. And well, it would take quite some time to understand this definition. Hopefully the problem that I will introduce next will be easier to understand. So now this is the main part of the talk now that will go on next, which is the introduction of this new tool, the PureCircuit problem. And I'll take questions after that. All right, so the PureCircuit problem, how is it defined? So it's a PPAD complete problem that can be used to prove hardness of Nash and many other problems, okay? So what does it look like, this problem? The input to the problem is a Boolean circuit, but with a twist, or with a few twists. The first twist is that the circuit can have cycles. Normally in a Boolean circuit, you don't have cycles because you want to be able to just evaluate the circuit. Here you have cycles, meaning that it's not an acyclic graph. And the fact that you have cycles is actually very important. The second twist is that normally in a Boolean circuit, the nodes just take values 0, 1, true, false. But here you allow a third value, which I denote by this perpendicular sign, and which I'll just call it garbage. Okay, so every node in the Boolean circuit is going to have a value that's going to be 0, 1, or garbage. And the third twist is that in addition to the standard logical gates that you usually allow in a Boolean circuit, like the NOT gate, the OR gate, the AND gate, we'll also introduce a new type of gate, which we call the Purify Gate. And we'll see how that is defined and why it is necessary. Okay, so the input is this, kind of generalized extended Boolean circuit. And the goal is, given the circuit, just find an assignment to each node such that all the gates in the circuit are satisfied. Okay, so I give you the circuit and you just have to assign values to all the gates so that so all the nodes, so that all the gates are satisfied. So of course, when I say satisfied, I have to define what that means, especially since I have extended the possible values with this new garbage value. So let's take a case, let's take a look at the different types of gates. So the NOT gate. What is a NOT gate? Well, a NOT gate is normally just a Boolean gate that takes, you know, the value false and outputs true. And if you input true, then it outputs false. So when we have a NOT gate in our circuit, what we'll do is that if the node that is the input to the gate has value 0, then the gate will be satisfied if and only if the output node has value 1. Okay, so you can think of this gate as computing the NOT function. If the input is 0, it outputs 1. Similarly, if the input node has value 1, then the output node will have value 0. Okay, so the NOT gate enforces that a 0 is turned into a 1 and a 1 is turned into a 0. I haven't defined what the gate does if the input is garbage. So let's look at that next. What if the input to the gate is garbage? What do we want about the output? And the answer is we don't enforce anything. Okay, the output node can have any value, meaning it can be 0, it can be 1, or it can be garbage. I don't care. The NOT gate does not care about what the output is if the input is the garbage value. It does not impose any constraint in that case. Let's look at a different gate, the AND gate, for example, that has 2 inputs and 1 output. What does the AND gate normally do? Well, it computes the logical AND of the 2 input bits. And this is what it's going to do here as well if the inputs are normal 0, 1 bits. So if I input 0 and 0, then the AND is going to output 0. If I input 0 and 1, then the AND is again going to be 0. If I input 1 and 1, then the output will have to be 1. And now I have to say what happens when the inputs are not nice pure bits 0 and 1. What if there is some garbage in there? For example, what if one input is 1 and the other one is garbage? Then again, I don't enforce anything. The AND gate has no constraint on the output. If one of the inputs is garbage, the other one is 1. The output can be anything. It can be 0, 1, or garbage. Now, one interesting case is what if the input is garbage and 0? And here's something interesting. We require something interesting. Here, the definition of the AND gate says that you should output 0. And the reason is that if you take the AND of something, of 0 with something, whether that is 0 or 1, doesn't matter what it is, the output should always be 0. Okay, and so we require that in the definition of our problem, we require that the AND gate enforces this, namely that the AND of 0 and garbage should be 0. Okay, we call this, you know, the robustness of the AND gate. And it turns out that this is actually very important. If you remove this, the problem is no longer PPAD complete. Obviously, if both inputs are garbage, the output can be anything. No constraint on the output. And now let's look at perhaps the most interesting gate, the new gate, which is called the Purify Gate. So this is a new gate we introduce, which, well, first of all, it's interesting because it has 1 input and 2 outputs. Usually gates are thought of as having a single output, but here we have 2 outputs. So what does this Purify Gate do? If you input 0, then it just outputs 0 twice. Okay, both outputs are 0. So it just copies the input. Same thing, if you input 1, it just copies the input. Both outputs are 1. Okay, and the interesting thing is what happens when you input a garbage value. When you input a garbage value, the Purify Gate requires you to output something that contains at least 1 pure bit value. Okay, so at least one of those 2 outputs, I don't care which one, has to be a 0 or a 1. You cannot output 2 garbage values. In other words, this thing is not accepted. The Purify Gate is not satisfied if you assign garbage to all those 3 nodes. Then you have not correctly satisfied the Purify Gate. But if you put a 0 here, then the gate is satisfied because you have one of the two outputs that is a pure bit. And of course, it could be a 1, or it could be over here, it doesn't matter. One of the two has to be pure, that's all. So let's look at some examples to get a feel for the problem. So I mentioned that the circuit has to have cycles for the problem to be interesting. Why is that? Well, let's look at a simple example like this that does not have cycles. I claim that the problem is easy to solve in polynomial time. Why is that? Well, essentially because you can just evaluate it like a circuit. Assign arbitrary values to the source nodes, to the input nodes of the graph. For example, 0 to both of them. And then just compute the rest of the gates. Because there are no cycles, you will never find something that breaks your earlier assignments. Okay, so you can just compute the gates. 0, the output has to be 1. On input 0, the Purify Gate just copies the input, and then you take the AND of 1 and 0, which is 0, and that's it. All the gates are satisfied, you've solved the problem. And this will work more generally if you don't have cycles. So cycles are really important. The second thing that we mentioned earlier, the second particularity of this problem, is that we allow nodes to take values 0, 1, and this new garbage value. What would go wrong if we only allowed 0 and 1? Let's take a look at this example, which is a cycle of 3 NOT gates. What happens if I assign 0 to this node? Well, then I have to assign 1 to this node over here. But then I have to assign 0 to this node over here. But then to satisfy this gate, I have to make this into a 1. And you can see that this is just going to cycle. And there is no assignment of values to the nodes that satisfies all 3 NOT gates if you're just allowed to use 0 and 1. With the extra garbage value, though, it's very easy to satisfy this cycle by just giving all 3 nodes the garbage value. Recall that if the input of a NOT gate is garbage, then the NOT gate does not care about the output. It can be anything. There's no constraint involved. And the third thing I mentioned earlier about this problem is, of course, the new gate, this Purify Gate. Now, why do we need this gate? What happens if we don't have that gate? So let's consider an instance that does not contain the Purify Gate, only uses NOT and, for example. And there is a very simple way to solve this instance, which is to just assign the garbage value to everyone. Okay, all of the gates except the Purify Gate, they're always happy if you just input garbage to them, then they'll be fine with anything as output, in particular garbage. So if there's no Purify Gate in your circuit, then it's very easy to solve it. So let's look at an example that has all those things, cycles, the Purify Gate, and where we can use all 3 values, 0, 1, and garbage. And I don't know, let's try to solve this instance. So how would we go about this? Well, we can, for example, start by putting garbage everywhere on this cycle on the left. So all these NOT gates are going to be fine. Now the Purify Gate is still okay with this, as long as we assign a pure bit value to this output. If we assign 0, 1 to this node, the Purify Gate over here is going to be happy. So let's assign value 1, for example. And then we can actually solve this thing as well by putting garbage in both nodes. Of course, we could have put 0 over here, and then we'll get a different solution. So this is how you would try to solve the problem, but this doesn't really give an efficient algorithm, and we don't believe there is an efficient algorithm because we can show that this problem is PPAD complete. Okay, so that's essentially the main contribution, the main technical contribution of this work, is that we prove that this very simple problem with just these 3 types of gates, NOT and the Purify Gate, is already enough to get PPAD completeness. This problem is PPAD complete. If you can solve this problem in polynomial time, then you can compute Nash Equilibrium in polynomial time. You can find market equilibria in polynomial time, etc. But of course, the most important implication of this result is that we can use this very simple problem now to prove PPAD completeness, PPAD hardness results for other problems. and in particular, very strong hardness results. So before I move on to the last part, which is the application, let me pause to ask if there are any questions about the definition of this problem.
I again have a small question. It's not a question about the definition per se, but is there some easy argument why there always needs to be a solution?
Yeah, that's a very good question. Yes. So if you look at if I give you an instance like this, I don't think it's obvious at all that why there should be a solution, right? So I can give you two answers. Yeah, it is a case that there always is a solution because the problem is PPD complete, so in particular, it always has a solution. But what is a way to see this? One not so interesting answer is that, well, in the application, we're going to reduce this problem to the problem of finding an equilibrium in a polymatrix game, and this is known to always have an equilibrium. So you get a proof of existence through that. But actually, there is a more direct way to prove existence of a solution by reducing to Brouwer's fixed point theorem. And well, I can try to sketch it in sketch the proof in words. The idea is that you're going to construct a function, a continuous function from, let's say we have n nodes in our instance, 1, 2, 3, 4, 5, 6, n. We're going to construct a function that maps the n-dimensional hypercube to itself, so 0, 1 interval to the n to itself, and in such a way that any fixed point of that Brouwer function, you can extract from it a satisfying assignment for this PureCircuit instance. And how do you construct that Brouwer function? Well, the idea is that you essentially implement the gates continuously. So for example, the NOT gate tells you that you have to map 0 to 1 and 1 to 0. And in between, you can do whatever you want. So the way you can think of it is that you're going to just find one continuous interpolation between those two things. So just define a function that maps the 0, 1 interval to itself, such that 0 is mapped to 1 and 1 is mapped to 0. And then you can just replace the NOT gate by that continuous function, and that would correctly implement the constraint. And you can do the same for all the other gates. There's a way to implement them by continuous functions so that they enforce the correct constraints everywhere where they have to satisfy it. And then the way in which you extract a solution from a fixed point of the Brouwer function is that you just say, okay, if the fixed point, so the fixed point is going to be an n-dimensional vector. If the ith entry, which corresponds to the ith node, is a 0, that means that the node must have value 0. If the value is 1, means the node has value 1. And if it's some value strictly between 0 and 1, then that gives you garbage. And by doing that, you will get an assignment that satisfies all the gates. What that tells you is that you can view this PureCircuit problem as some kind of a discrete Brouwer in disguise. Okay, meaning that you can think of this as an n-dimensional Brouwer function, but where you just really define what the function does with very, very few constraints. So you leave a lot of freedom into what the function looks like. You just constrain it at some very specific points. Oh, if that thing is 1, then that thing has to be 0. Or if it's 0, then the other thing has to be 1. If it's something in between, then I don't care what the output is. So it's a very undefined Brouwer function, which you can make into a normal continuous function by just picking one specific interpolation. And in that way, you can then show that there exists a solution. The reason why we want it to be underdefined in that way is because we want to reduce from this problem. And the fewer constraints the original problem has, the easier it is to reduce from it. So this is a tool to reduce from, mainly. But yeah, that's a very, very good question. Why does this thing always have a solution? It's not obvious. All right, let me move on then to the application. So the application is going to be polymatrix games. What is a polymatrix game? So a polymatrix game is a game with many players, n players, and we're going to think of n as being large. So there's many players n, And every player, to keep things simple, we'll just say that every player has just two possible actions, which we'll call 0 and 1. So every player just plays one of his two actions, either 0 or 1. And what that means is that the number of outcomes of the game, or also called pure strategy profiles, is 2 to the n, because there's n players, every player has two possible actions that they can take. So overall, there's 2 to the n possible outcomes of the game, if you want to specify what each player does. Now, this is, if you want to specify the payoff for each possible outcome, the payoff to each player for each possible outcome, that will be, exponential size. So that's not a very interesting problem because it has an exponential representation. So polymatrix games are a special case of these many player games that have additional structure which allows you to succinctly represent the utilities, the payoffs of the players. Okay, so in other words, the utility that a player gets from the game is the sum of the utilities that the player gets from some small games that the player plays with each other individual player. So instead of the payoff depending on some combinatorial way on exactly what everyone else plays, it is kind of additively, it can be decomposed additively so that the payoff that they get is just the sum of the individual payoffs with each player. And this then gives a succinct representation because you just have to specify what these individual games between the players look like. And there's just n squared of these games, and they're just 2 by 2. There's two actions for each player. So you can think of these as just being, 2 by 2 matrices, and you just need n squared of those 2 by 2 matrices to represent the whole game, which is efficient compared to 2 to the n. Okay, so these are some games with this natural structure that makes them succinctly representable and thus interesting to study. So we can think of this also as a graph where each blue node represents a player and the red edges represent interaction between two players. And so if you look at this player at the bottom here, the blue player here, the payoff that the player gets for a specific outcome of the game is just the sum of the payoffs that the player obtains for each of those red edges, for each of those interactions. And as I said, you just have to specify what the interaction is on each of those red edges. And that is polynomial as opposed to specifying a value for each possible outcome because there's 2 to the n of them. So the computational problem that we're interested in here, or the solution concept that we're interested in here, is a Nash equilibrium. So in other words, we want to compute a Nash equilibrium of a game, of a polymatrix game. What is a Nash equilibrium? I'm not going to define it formally. Just intuitively, it's a set of strategies, one for each player, where every player believes that they play the best that they could, given what the other players play. In other words, given what strategies the other players have picked, I am playing a best response to that choice of strategies. I am playing the best strategy I can play in order to maximize my payoff, given what the other players have chosen to play. Okay, and Nash's theorem says that there always exists at least one mixed Nash equilibrium, where the mixed here means that we have to allow the players to randomize. So the players recall that they have two strategies, two actions, 0 and 1. We have to also allow them to play randomly between the two, so to pick a distribution on these two strategies. For example, I play the first strategy with probability 1/3 and the second strategy with probability 2/3. If you allow the players to pick randomized strategies, mixed strategies, then a Nash equilibrium is always guaranteed to exist. And this is a very celebrated result in game theory. And now as a computer scientist, when you see this kind of result, you immediately think, okay, this thing is guaranteed to exist. It's a very important solution concept, but can I actually compute it? If you give me a game, can I actually find this Nash equilibrium? Can I find it efficiently in polynomial time? Or if I cannot find an exact one, can I at least compute an approximate Nash equilibrium? These are all very natural questions. So we will be looking at approximate Nash equilibria, and to be more precise, so-called epsilon well-supported Nash equilibria, which is one way to define approximate Nash equilibria. And again, informally, what that is that it's a set of strategies, one for each player, where each player plays only strategies that are epsilon best responses, meaning that they are epsilon optimal. And let me just mention that the epsilon here is an additive term. So this is an additive approximation, meaning that the smaller epsilon is, the better the approximation is. So if epsilon is equal to 0, a 0 W SNE is the same as an exact Nash equilibrium. On the other hand, if epsilon decreases, it means that it becomes a worse approximation of a Nash equilibrium. So people have studied this problem of computing approximate Nash equilibria. And it turns out that it's not too hard to come up with an algorithm that computes a 1/3 approximation. So that solves the problem for epsilon equals 1/3. And let me just briefly say what the algorithm does, because it's quite simple. So the idea is you look at your game, at your polymatrix game, and you just try to find a player such that one of his two actions, 0 or 1, is always a 1/3 best response. Meaning that no matter what the other players are playing, if this player plays that action, it will always achieve at least, a 1/3 additive approximation to the best thing he could do. Okay, and once we've found such a player, we're going to fix the player strategies to play always that action, that pure strategy. And we're going to remove the player from the game and repeat. Okay, so at some point, we won't be able to find such players anymore. In fact, even when you start over the beginning, maybe such a player does not exist. So what would you do once you get to a game that doesn't have such players anymore, where you cannot remove any players by having them play pure strategy? Then you just let all the remaining players mix uniformly. So they just play the strategy that plays action 0 probability 1/2 and action 1 with probability 1/2 as well. Okay, so the idea is just eliminate players who have a pure best response, a 1/3 best response, and then let the remaining players just mix uniformly between the two actions. And it turns out you can show by direct computation that this always gives a 1/3 Nash equilibrium. Okay, so this is a pretty simple algorithm. I would say it's one of the very natural things to try out when you first see this problem. And the obvious question is, can you do better than this pretty naive algorithm? And if not, can you provide some evidence that, there's a reason why we cannot do better? So here, because the problem of computing a Nash equilibrium is in PPAD, cannot go showing NP hardness, you have to stick with PPAD hardness. So what is known about this problem? There are some PPAD hardness results. So in fact, the celebrated results on Nash equilibrium, they essentially use these polymatrix games as intermediate results in order to get to bimatrix games. And the paper by Deligkas, Kohlberg, and Papadimitriou already essentially implicitly proved that computing an epsilon Nash equilibrium in polymatrix games is PPD complete for very small epsilon, meaning inverse exponential epsilon. So as the instance of the game becomes larger, the epsilon has to become smaller at an inversely exponential rate in order for the problem to remain PPD complete. The paper by Chen, Deng, and Tang, which prove hardness of computing Nash equilibrium for two-player games, bimatrix games, again, implicitly prove this to inverse polynomial epsilon, meaning that the epsilon has to decrease as the instance increases, but at a slower rate. Okay, and finally, there was a breakthrough result more recently by Rubinstein, who proved that there exists some constants so that the problem remains hard. Okay, some absolute constant, so that no matter how the instances become larger, the same constant, for the same constant, the problem remains PPAD complete. So this, this was a state of the art before the introduction of the PureCircuit problem. Now, if you look at this statement, it does tell you that the problem is hard for some constant. So it tells you that there's no PTAS, no polynomial time approximation scheme. But what's a bit unsatisfying is that it just says there exists some constant, and it doesn't tell you what the constant is. And if you try to go look into the paper of Rubinstein, he does not mention a constant. And the reason is that because the proof is very complicated, the constant that you would be able to extract from that would be very, very small. And I would say, insignificant for economic or game theory applications. There's a question in the chat.
Yes. So
is the constant epsilon computable? Yes. So you can go look at the proof, and you could find some low bound on the constant. So you could find some explicit expression for the constant. The problem is that it would be something very small. I don't know, 10 to the minus 10 or something like that. Because this is a natural problem, computing a Nash Equilibrium, we would like to know what happens for actual realistic constants. And so we have on the one hand this 1/3 upper bound and this very, very small lower bound. And so what the PureCircuit problem allows us to do is that it allows us to get a tight result here. Maybe it allows us to show that for any constant that's strictly less than 1/3, the problem immediately becomes PPAD complete. In other words, this relatively naive algorithm that we saw earlier is the best you can do if you want to solve the problem in polynomial time. As soon as you go below 1/3, the problem becomes intractable. And the tool that enables us to prove this stronger result is this PureCircuit problem that we saw in the previous part. So in other words, in order to prove this theorem, we have to show that for any epsilon strictly less than 1/3, you can come up with a reduction, polynomial time reduction, from the PureCircuit problem to the problem of computing an epsilon equilibrium in a polymatrix game. And in the few minutes that I've got left, let me just sketch how that goes. Before that, let me mention that actually this is not a one-off. Turns out that for another class of succinct games, which are called graphical games, we can also get tight inapproximability results. I think this provides further evidence that this PureCircuit problem really has something that allows you to get these tight hardness results. And that's why we believe that it really captures the essence of PPAD hardness. It's kind of the simplest problem to reduce from in order to prove PPAD hardness. So I'm not going to talk more about these results. Let's go back to the original 1/3 hardness that we want to prove. So we want to reduce from the PureCircuit problem to the problem of computing an approximate equilibrium for a polymatrix game. This means that given an instance of PureCircuit, we have to provide a polynomial time construction that gives you a polymatrix game. And the reduction is going to be quite straightforward. Okay, so we're given this instance of PureCircuit. And what we're going to do is that we're going to create one player for each node of the PureCircuit instance. Okay, so this is just going to be a one-to-one thing. For every node of the PureCircuit instance, we create a corresponding player in the game. Every player is going to have two actions, 0 and 1. And the interpretation of these actions is also going to be very natural, where we're going to map back solutions, meaning that if at a Nash equilibrium a player plays action 0, then we simply interpret that as telling us that we should set the node to have value 0, the corresponding node in the PureCircuit instance. Similarly, if a player plays the action 1, then the corresponding node in the PureCircuit problem should have value 1. And finally, if a player mixes, meaning randomizes between the 0 and 1 actions, then we'll interpret that as saying that the node value, the corresponding node, should have value garbage. Okay, so this is how we map back solutions. In a picture, if this is our original PureCircuit instance, then we construct a polynomial time, a polymatrix game where there is one player represented as a blue node corresponding to each node of the original instance. And then we have to define what the interactions between the players are in such a way that the gate constraints are implemented meaning that if we map back the values, as I explained, according to these rules, that the original gates are correctly implemented. And it turns out that this is not too hard to do. I won't go into detail, just give you an idea of what it looks like. So if you originally have a NOT gate between this node and this node, and this is the player corresponding to this node, and this is the player corresponding to this node, then you will define the interaction between these two players, namely the game that they are playing between them, as follows. So this represents a payoff matrix, giving you the payoff for each possible outcome of this local two-player game. So the top right is the payoff for player U, and the bottom left is always the payoff for player V. Okay, so this completely defines the interaction between those two players. If U plays 0 and V plays 1, then we go in this square, and we see that U gets value payoff 0, and V gets value 1 in that case. Okay, so this game is not just a randomly constructed game. This is exactly the way in which we have to define the interaction between U and V so that the NOT gate is implemented. What do I mean by that? If the U player plays the 0 action, action 0, then in order for V to best respond, he has to play action 1. Similarly, if U plays action 1, then by analyzing this game, you can easily show that V has to play 0. And importantly, this doesn't hold only for exact best responses, but for epsilon best responses. And actually, this works for any epsilon less than 1. So the gates that we implement later will put more constraints on epsilon to take us down to strictly less than a third. But for the NOT gate, it's very easy to implement it for any epsilon. Okay, so by constructing the game in that way, we ensure that at any Nash equilibrium, since V has to best respond to V, the strategies have to satisfy essentially the PureCircuit constraint of the NOT gate. Similarly, you can implement the other gates. So if you have an AND gate somewhere, and these are the corresponding players corresponding to the nodes, then you're going to define the interaction between those two players. And it turns out that you just need to define interaction between U and W and V and W. So you have those two matrices that represent the payoffs. And again, these are constructed in such a way that at any Nash equilibrium, the strategies of these three players, if you map them back to values for the nodes, they exactly satisfy the constraints of the AND gate. And now note that this gate works for any epsilon strictly less than a third. Obviously, I'm just showing this reduction as an illustration. I don't expect you to check these pairs or anything, just as an example of how reduction would go. And finally, we also have the Purify Gate with these are the corresponding players. You can again construct locally. You can come up with payoffs for these interactions that ensure that at any Nash equilibrium, at any epsilon Nash equilibrium for any epsilon strictly less than a third, the values, the strategies are mapped back to values for the nodes that exactly enforce the Purify Gate. And again, this works as long as epsilon is strictly less than a third. So that's all I had in mind, just showing you an example of how this reduction works. I think that really the main thing that I wanted to show you is the definition of the PureCircuit problem, because I find it very elegant, quite simple to define. And so hopefully easy to use to prove future PPAD hardness results, whether these are tight inapproximability results or just simpler reductions. That's all I had. Thank you.
All right. Thank you very much for that talk. Are there any questions? That does not seem to be the case. So thanks again for the talk.